Hello, my name is Kevin McCall. Welcome to the event. I work in a developer relations capacity for NVIDIA. I've actually only been at NVIDIA a few months. NVIDIA, I was with Microsoft almost 26 years. The last 10 years mainly focused on AI. So today we're going to talk a little bit about AI generally, of course, but generative AI more specifically, and talk about how that's not only pretty fundamentally changed our collective attack surface, you might say, that we have to defend, but it's also changed the TTPs of our adversaries as well. So I'm going to talk a little bit about how we're using generative AI internally, how we're thinking about these workflows and workloads, and talk a little bit about some projects that we've done internally and what we've learned from them in how we not just deploy generative AI applications, but how we've learned to better secure them by virtue of working them directly. Now, here's the overall agenda. At a high level, I'm going to briefly touch on what we consider to be a virtuous flywheel of deploying and working with and learning about these technologies that allow us to subsequently improve them and overall reduce our security risks over time. Talk a little bit about the strategies, tactics, and specific tools that have been used as of late by our cybersecurity AI team, managed by Bartley Richardson out of the East Coast. And then I'm going to go through 3 projects that we've done internally. All of these projects have assets that have been posted to GitHub. So if any of this looks interesting to you, you can go up there and and download not just bits, but read all the documentation and things like that. Now, given the time constraints today, some of this I will necessarily cover at a high level, but I'll try to inject suggestions and references to where you can learn more if any of this looks interesting to you. So why don't we go ahead and get started then? I'm not going to cover this entire slide in detail, but I would suggest that the most important meta point is right in the middle, you might say at the top and the bottom, where on the left, if we think about deploying new generative AI applications, as we are doing, and other enterprises clearly are, as we create and then deploy these new generative AI applications, and we do our stride attack vector models, we deploy them, secure them, manage them, and monitor them over time, then we're taking everything we learn by working with these applications in deployment and everything we're learning as we need to secure them and monitor them. And we're using that effectively to inform both functional and non-functional requirements for future products and future projects. And so if we use that as a set of inputs in order to improve these applications and these deployments, we then prioritize deploying new capabilities that we're developing as a result of that input, thereby essentially creating this virtuous flywheel, you might say, where we fumble through the deployments, we learn how to best manage and monitor them over time, and then we use all of these learnings in order to inform these improvements. Now, relentlessly executing this iterative circle is definitely in our DNA at NVIDIA. This deeply defines us. But another thing that's in our DNA is really thinking about these improvements and tackling them from what we call a full stack, approach. People know of NVIDIA as a GPU company. We are. People think of NVIDIA more recently as an AI company. We definitely are. But it's actually more accurate to think of NVIDIA as an accelerated computing company. And in order to dramatically accelerate the execution of workloads, I'm not talking about 20, 40, 60%. I'm talking about order of magnitude improvements in workload execution. You really have to think about and approach these challenges in a full stack way. So it definitely starts with maximizing the use of highly specialized hardware at the bottom of the stack. And it's not just the GPU, it's also specialized CPUs. Yes, we do design and build CPUs, but also the DPU, what we call the data processing unit. So it starts with having all of that specialized hardware. having specialized networking hardware that sits on top of that that can connect all those together at insanely high bandwidths. But then we proceed up through the stack to CUDA libraries and what we refer to as our CUDA-X libraries that take maximum advantage of the parallelization afforded to us in those underlying specialized hardware components. But then marching up through hundreds of AI models that we publish for partners and customers, all the way up to the top in what we refer to as workflows, which I'll talk about in a moment. But in summary, as we think about improving and iterating on this virtuous flywheel, we're thinking about everything in a full stack way. And I'll offer some comments and some other examples of how this manifests itself in some of the projects that we've done. So if I were to attempt to channel, imperfectly certainly, our cybersecurity AI team, then some of the themes you're going to hear from them pretty frequently are these ideas of accelerating workloads. Accelerating workloads is always unambiguously a good thing, right? We always want things that take days or hours to happen in minutes or seconds. We clearly and also unambiguously want to reduce the number of cycles that either our SOC analysts or our security engineers have to spend on problems in order to get their jobs done. And if you kind of logically multiply those two together, then the goal clearly is to dramatically shift the detection window to the left, right, on our calendar. But in addition to those two, generative AI has afforded us some new tools and approaches that allow us to add net new capabilities. And so if we skip all the way to the right, most of what you're going to see in the middle is pretty either self-explanatory or already covered. If we go all the way to the right, then some approaches or tools like synthetic data generation using recent developments in large language models, or agent-based workflows, again, also frequently sitting on top of large language models, as well as RAG patterns, Retrieval Augmented Generation patterns that allow us to make best use out of all the content and the knowledge our enterprises contain. These are tools or tactics that have become quite mature and quite valuable lately. And in the examples I'm going to go through, I'm going to talk about how we've used all three of these on these projects, multiple of them in some of the projects. So I'm going to go into more detail on that at this time. Now, before I get to the actual project discussions, let me just come back to this concept of a workflow. As I mentioned, we think about all of these problems in a full stack way: specialized hardware, world-class hardware at the bottom, and then putting the right libraries on top of that world-class hardware so that ISVs, partners, customers can build great systems, build great applications that take advantage of the massive parallelization and specialization of the hardware. But as we go up through the stack, through the specialized libraries to hundreds of AI models, at the top of that stack are these logical workflows. Now, workflows, unsurprisingly, think of them as prepackaged reference applications that have assets as well as documentation that really bring together a number of different things, oftentimes multiple models and services, to solve a well-defined problem. And now sometimes those are security problems, and some of them are non-security problems, of course, right? Now today we're clearly going to focus our attention on security specific problems. So things like vulnerability and exploitability analysis, some challenges around AD, and we're also going to talk a little bit about spear phishing. And so all of these come together in these published workflows that outline how you can use a number of different assets and bring them all together in order to tackle some of these thorny and perpetual problems. So if we jump right to these three examples now, and again, I hope and I expect that my coverage of these topics will leave you wanting more detail, and I will give you links to where you can find a lot more detail on all three of these projects. But let's start with AD. So one interesting project that we did recently to attempt to much more quickly and accurately detect anomalies across our network was this project we refer to as digital fingerprinting, right? I'm sure you've heard that term before. And kind of the meta idea is, how do I create a specific model, a unique model that represents normal behavior for that actor or that asset? So this could be a user, or it could be a server or a service that spans multiple servers. For our purposes today, let's talk about users as actors. And that's where we started our investigation in this space. But it could be either. It could be an actor or an asset. But the idea is, how do I take historic events? How do I take telemetry that's specific to that actor? We'll just use the user concept from here on out. And how do I use latest developments in AI to create a unique model that represents normal, right, for that user? And so in this case, if we kind of focus on the bottom on the training time first, we want to take hundreds, if not thousands, of these events, network events, file access events, privilege escalation events, generally auth in and auth Z behavior all up, right? But it's across the board. It's all of this type of telemetry. And what we end up doing is training time is that we take all of these events and we learn, we basically learn an AI model. We use an unsupervised autoencoder in order to learn a model that can encode and decode all of that, those events that are specific to that user. So yes, that means at NVIDIA, for example, this would result in the creation of 30,000 models, right? One per employee, right? And so this does represent, thankfully, it's not billions or millions, but it's thousands of GPU hours. But we are learning a model per user. So now we have 30,000 models that have been learned to effectively encode and decode what behavior looks normal for all of those users in this case. And then we store all of those models in the MLflow repository. So if we pivot over to then runtime, what happens in production is that we'll stream in events in near real time. We take those events and we encode them using the exact same autoencoder that we used to initially train these models per user. What that autoencoder does is that basically by encoding that traffic, it then can emit a probabilistic estimate of how abnormal that behavior is. So to be more specific, it will actually output a z-score that logically is the number of standard deviations away from the mean that traffic appears to represent. Now, you can set the thresholds in all sorts of different ways, and you can decide what to do with that. But the meta goal here clearly is to have a lightning fast and a data-informed way to output a scalar, right? This z-score that allows you to infer how anomalous this event looks. And then you can take it and do whatever you want to do with it with regard to providing a prioritized list of things to your SOC analysts that they may want to investigate. And we've adorned this slide, you might say, with some of the tools that this pipeline, this Morpheus-based pipeline, out of the box integrates with in order to present some of that back to you. There's great content online that goes into a lot more detail on this example, both technical blogs and sessions that I'll give you links to a little bit later. So if we go to the second example, this is an interesting problem because phishing is one thing, but clearly spear phishing is an entirely different thing. This is a domain where if you're thinking about this from an AI perspective and a data set perspective, this is a great example of where there aren't, and maybe there can't be, really good public data sets for training AI models that can detect spear phishing attempts. By definition, a spear phishing attempt is highly specific to your industry, your company, even the current leaders at your organization. So literally the names and the boxes on the org chart today, right? By definition, a spear phishing attempt is going to be a function, quite direct function, right, of all of that. That's highly, obviously, company specific. And so the way we tackled this problem was starting with rich synthetic data generation in order to attempt to create a really useful data set that was company specific in this case. So we used some extensive and fancy prompt engineering on top of our Nematron model that's really good at generating synthetic data. Now, our Nematron model is pretty big. It's pretty powerful. It's a 340 billion parameter model, but it's available, for use online. And so we created the prompt engineering with the intent, in this case, no pun intended, of synthetically generating millions of phishing attempts that were in these various, what we refer to as intent categories. There's 3 listed on this slide, but you can have an arbitrary number of intents that you're sniffing for, you might say, in those incoming emails that could represent potential phishing attempts. So we basically do the prompt engineering. We synthetically generate millions of messages that are in one or more of these intent buckets. And then for each one of those piles, you might say, of synthetically generated email data, we train an encoder model. So specifically, these encoder models were based on the BERT architecture. You may have heard of BERT. It was kind of the OG encoder model that came out based on the 2019 paper. Specifically, we used the DistilBERT architecture, which is a smaller version of the BERT architecture. And for each one of the unique intents that we're attempting to observe in these incoming emails, we train an individual DistilBERT model. So by definition, one DistilBERT model per intent that we're attempting to observe in these incoming emails. Now we also have a database that, again, at development time, you might say, at training time, we take a whole bunch of historical email messages, and for the sender and receiver pair, we store a ton of attribute information. When did the sender send these emails to the receiver? Literally, what were some of the syntactical attributes of the content and the body of the email? How formal or informal was the sender's voice, in that email message? Lots of other stuff that we take out of those email messages and store them into a database so that we can look them up later. We then have, beyond the models that allow us to observe intent, we also have a logistic regression model at the end, right, that acts on all of this data at runtime. So I'll walk through that in a moment, but there is one model per intent type. Those are the DistilBERT models that I mentioned. But then in the end, there's also a logistic regression model that takes everything that we know and everything that we've observed and then attempts to assign a probability score for our belief that this is indeed a spear phishing attempt. Okay, so at runtime, let's walk through how this would work. Email comes in. The email would be run through each one of these DistilBERT models. Each one of the DistilBERT models will then output a confidence, a probability figure, a scalar that represents whether or not it believes that that intent was present in that email message, right? There are obvious confusion matrix implications here for false negatives, but that's kind of beyond the scope of our discussion today, and clearly that has to be tackled. But keeping this at a high level, the email comes in, it runs through each one of those DistilBERT models in order to get a probability figure for each one of them. In parallel, we're looking up information that's in this Postgres database so that we can look up information that has happened prior between that sender and that receiver. So when did that sender send email to this receiver before today. Again, some of those syntactical attributes. We package up the output of these Dilbert models with what we look up in our database. We put all that together, enrich it, and then we run that through a logistic regression algorithm in order to come up with what we essentially are inferring as a label, that label being our confidence and what ends up being a binary classification on whether or not we think this is a spear phishing attempt. Now, what you do with it is up to you. The way we did this internally is we had thresholds of confidence, and then we took those thresholds of confidence and we adorned the email message in different ways in order to alert the user that the system believed that that was a potential spear phishing attempt, right? You can do, of course, whatever you want with it. We basically used a prefix, step in the overall pipeline to perform this evaluation, inspect the output, and then if we had a high confidence it was a spear phishing attempt, then we would change the subject line, put a header in the email, and then provide some buttons in there so that after the recipient of the email did their own, out of band evaluation on whether or not it was a spear phishing attempt, they could provide feedback to us to improve the models. That's as far as I'm going to go in the detail. I do think it was noteworthy that when we did this project, after the first round of training, you might say, we synthetically generated these millions of messages, we trained these Dilbert models, and we took a test set that was created by our red team. It was a highly curated, very high quality set of email messages that our red team had created to try to test the system. And after the first round, the system identified more than 70%, correctly labeled, correctly classified more than 70% of those messages that were curated by our red team. But then what we did was we took all of the ones that it had misclassified, and then we improved some of our prompts, and we generated more synthetic messages that tried to increase the not just the quantity, but the quality of our data set that were focused on those intents. And then we retrained the models, did it a second time. I think that the second time we were at about 91% accuracy on the classification of those messages. And we did the same process again and generated more synthetic messages, retrained the models. And then on the third pass, we got to nearly 100%, correct classification based on the curated data set that was provided by our red team. So if we go to the third project, this is what we affectionately refer to as the CVE vulnerability and exploitability analysis analytics workflow. Clearly, that's a mouthful. You won't see these words many places online. You probably will see it branded under Agent Morpheus. So our marketing team, of course, took all of these syllables and condensed it down to Agent Morpheus, which is shorter and clearly a lot sexier than this moniker. But the problem we were trying to solve here is we were trying to automate the best we could the analysis of understanding for each container in deployment within our enterprise. When new CVEs were posted, we wanted to be able to automate the analysis of whether or not that CVE, that vuln, was present and exploitable across all containers where it potentially applied. Clearly, security engineers spend many, many hours doing these types of investigations. They're highly iterative, they're very detailed. And what we attempted to do here is automate as much of it as we could, but keep a human in the loop at the end. So what we ended up doing, and yes, this is a very high level diagram. We have much more detailed diagrams in some of the online sessions that I'll refer you to on the next slide. But the way we approach this is first, we took a ton of enterprise content, everything from, of course, internal documentation, software bill of materials documentation, GitHub repos, a ton of other content. And then we ragged it, you might say. We took it through a retrieval augmented generation pipeline to create vector embeddings of all of that content. And then we stored all of those vector embeddings into a vector database. So then we created 4 different agents. Now, all of these were large language model based agents, but they had dramatically different personas. The first model basically did the initial evaluation and generated a checklist. So basically, it went out to the NIST, CVE, website. It went out to the distro specific, CVE documentation. It went to a number of other locations, and it basically learns enough about the CVE in order to generate a checklist around what a security engineer should or could do in order to thoroughly investigate the situation for a given container. So the first model outputs this very, very detailed checklist. The second model then takes that, and the second model's goal is to iteratively go through that entire checklist, generate prompts, reach out to various systems, internal and external, and basically do all the detective work on whether or not it believes or it finds the vulnerability in that container and understands whether or not that vuln is exploitable or not within that container. So the output of the second model is everything that it's learned, right? The result of all of its detective work, right? So then it hands it off to a third model. A third model consumes the output of model number 2. And the third model creates a structured summary of everything that's been learned. So think about that as templatizing, you might say. We've, templating the output of model number 2 and creating a very predictable, structured set of learnings that came out of the efforts of the second large language model. So that's what the third model outputs. Then there's a fourth model that consumes that structured summary and makes a recommendation on what to do with that container. And it also writes up a VEX document. So it generates a VEX document that then is all packaged up and dropped onto a queue and handed to a security engineer. So in short, we're trying to essentially rag all of this information that's very valuable, create specialized language models to automate this workflow. This is a long-running workflow. It takes almost 2 minutes to run end-to-end at the speed of light, you might say. So there's hundreds and hundreds, oftentimes 500 or 1,000 different system or accesses that are occurring internally and externally to learn everything it needs to learn. But then in the end, there's always a human in the loop. There's always a security engineer in the loop because we drop all this back onto a queue, present the results, and then have a security engineer review the output of this analysis, read the VEX report, and decide, what they believe needs to happen. So this is, Bartley covers this in a lot more detail in his GTC session in March, which is really wonderful. I highly recommend going and watching his session from March that's freely available online on our GTC 2024 website. So I'm going to stop here. Here we have a number of links that go to technical blogs that describe some of these projects that we've done, hands-on labs, hands-on workshops. There's also good data around some of the really massive speed up that we've been able to deliver on some of our internal workloads as well. And like I mentioned, approaching some of these challenges from a full stack perspective, allows us to really think in terms of where can we deliver, order of magnitude greater throughput on some of these workloads. And so Bartley goes into some good details in his session as well, where he'll talk about how, for example, for one workload, we had 416 virtual machines, each one with one CPU that was doing a lateral movement detection workload. And we were able to take that 416 CPU effectively workload and move it to a single virtual machine. It was a much bigger virtual machine. It had 4 GPUs, but we were able to take this 416 VM, 416 CPU workload, move it to a single 4 GPU infrastructure, and dramatically speed up the process while saving almost 80% on our overall TCO for that workload. This is one of many examples that we go into in more detail in some of this online content and some of the online sessions. So I will leave you there. Hopefully this was interesting to you. I welcome any feedback, and we welcome any feedback regarding how you're using some of these assets in the real world, and where you think we should take some of this content and some of this development moving forward. So thanks for your time. Hope you have a good rest of the conference.